Hello my people, I hope we're doing well today. We're going to go ahead and get started on 4.2 with this video. 4.2 is usually titled the mean value theorem, and I will get to the mean value theorem in just a moment, but I need to do a little backtracking, okay? Now, we have talked right when we started doing derivatives about the secant line, right? And the job that the secant line did for us is the secant line gave us an approximate slope, okay? So if I have something like, that function right there, okay, and I'm interested from A to B, okay, and I have those 2 points right there, I know that the secant line here can give me an approximate slope for that particular slope at that point right there. Now, it's not a very good one, and of course the closer that B is, the better the approximation, right? That's the whole logic behind finding the derivative by limits, right? Is to take this distance right here and shrink it down. That is using the secant line as in order to get an approximate slope at any particular point. So if I wanted to find an approximate slope at A, but I didn't know the derivative, or I didn't have the function itself, I was just given like data that basically a certain situation modeled, I would find a secant line close by or surrounding that point in order to find an approximate slope. Well, another thing that the secant line does for us is it gives us average slope, okay? So f of b minus f of a over b minus a, of course that winds up being the secant line, okay? And that is going to give me either one, an approximate slope, okay, for either A, B, or any point in AB, but it can also give me the average slope over that interval, okay? So it's the average slope on AB, okay? Now that winds up being pretty significant, okay? So what the mean value theorem actually says is this. If I'm given, two things need to be the case. If, number one, okay, f is continuous on an interval a to b, okay, and if f is differentiable, meaning for the most part a smooth curve, okay, on a to b, okay, then there exists some value in AB that we'll call C, okay, then there exists a value C in AB such that f prime of C is equal to f of B minus f of A over B minus A. Now, I'm going to unpack that. And I'm going to unpack that by an example. Let's say that you get started driving and you're going to head off to San Antonio, okay? And let's say that they built a new toll road to San Antonio, and you get in it, it's 100 miles long. The toll road's 100 miles long. They have a picture of you entering the toll road at a specific time, and they have a picture of you paying at the end of the toll road, exiting the toll road at a specific time. And when you exit, a cop pulls you over. And he says, well, I tell you what, I'm going to give you a ticket for going 100 miles an hour. And you say, well, why? And he said, well, that toll road is 100 miles long. and you entered the toll road at 10 a.m. and you exited the toll road at 11 a.m. and you averaged 100 miles an hour. And you say, well, just because I averaged 100 miles an hour doesn't mean I ever went 100 miles an hour. And he says, aren't you in calculus? Doesn't your teacher teach you the mean value theorem? There had to have been a point somewhere in the interval where the instantaneous rate of change is equal to the average rate of change. Okay? So if f is continuous and if f is differentiable, then there exists a value c, at least one, in the interval such that the slope at that moment is equal to the average slope over the interval, okay? And so let's go back up to this example that we have here. Is there a point in AB? Now this curve right here, it is continuous and it is differentiable. Now it doesn't have to be continuous and differentiable over its whole implied domain. It just has to be continuous and differentiable over the interval that's being interrogated, okay? Now, on this interval, it is continuous. On this interval, it is differentiable. Okay? So the two hypotheses have been satisfied. There has to be a value inside here where the slope at that moment is equal to the average slope. Or another way of putting it, there has to be a point that has a tangent line parallel to the secant line. Okay? And you can sort of ballpark it and say, yeah, it looks like right about there I'm going to have a tangent line that is parallel to the secant line. Okay? And so you see the tangent line here, and that point right there we'll call C. Okay? So because it's continuous and it's differentiable, there is required, and there could be more than one, but there has to be at least one. There has to be at least one point in the interval where the instantaneous rate of change, the slope at that moment, is equal to the average rate of change, or the average slope over the interval. Okay? And you're thinking to yourself, that sounds an awful lot like something that we've done before. And you'd be correct. Okay? That is an awful lot like the intermediate value theorem. Okay? The intermediate value theorem was, and I told you this when I introduced it back in Algebra 2, it was the first of its kind that you've seen. The intermediate value theorem said this. Value theorem. Okay, and actually, when you get to the AP exam, if an answer or a justification requires intermediate value theorem, you can abbreviate it IVT, intermediate value theorem. The mean value theorem, you can basically abbreviate MVT. They will take that as a legitimate answer. Okay. So the intermediate value theorem, remember it was that one that said in order to go from here to there, I have to pass through every point in between. Okay, and it specifically was introduced during the section on polynomial functions, and it helped us to find zeros, right? But basically, if I'm dealing with a polynomial function, or more generally just any continuous function, if f is continuous, okay, on A to B, okay, if f is continuous on A to B, and that implies that it passes through every single point here, okay, and remember, continuous means I can draw it without picking up my pencil, then basically if f is continuous on AB, then in order to go from A to B, I have to pass through every point in between f of A and f of B. Okay? So basically that's a nice way of saying to go from here to there, if it's continuous, I have to pass through every single value here, and I have to pass through every single value here. And that was the first of its kind that we saw, and I told you that this was going to be the first, and that it would basically foreshadow ones that were to come. Well, we're there. The mean value theorem is the thing that fulfills that foreshadowing. So let's go ahead and do an example. We're actually getting towards 10 minutes right there, but I think it's important to sort of give you the backdrop of all of this. Now, let's go ahead and let's look at y is equal to x over x plus 2, and I want to figure out whether the mean value theorem applies for this function on the given interval, and if so, I need to find the value of c which satisfies. Okay, so just by way of review, I need to determine whether f is continuous on AB, whether f is differentiable on the open interval AB, okay, and if it is both of those things, then there is a value of c where the rate of change at that moment is equal to the average rate of change, okay? And so, is f, or y in this case, well, let's go ahead and scratch that out and call it f. That's fine with it. Is f continuous? Well, f is not continuous everywhere, but where is f discontinuous? F is discontinuous at x is equal to -2. Well, is -2 inside this interval that I'm concerned with? No, it's not, okay? And therefore, I know that if the only place where f is discontinuous is at -2, then it's continuous on this interval. So f is continuous on 1 to 4, okay? And you know what that looks like from 1 to 4, most likely, but let's go ahead and take the derivative. And I'm going to get x plus 2 times 1 minus x times 1, all of that over x plus 2 squared, and that winds up being 2 over x plus 2 squared. Now, in order to determine whether f is differentiable, if f is differentiable on 1 to 4, that means that its derivative is continuous on that. Is f prime continuous on 1 to 4? Yeah, because it has the same point of discontinuity as the original, the -2, and it has no additional points of discontinuity. So you've recognized the fact that f is continuous on 1 to 4, the closed interval. F is differentiable on 1 to 4, the open interval. Now I know that I need to figure out what value inside here gives me a instantaneous rate of change that is equal to the average rate of change. Well, the first thing that needs to happen is I need to find the average rate of change, right? So let's go ahead and find that average rate of change, okay? And that's going to be f of 4 minus f of 1 over 4 minus 1. Well, f of 4, go ahead and plug that in. It's going to be 4 over 6, or 2/3. Okay? Plug 1 in, and you're going to get 1 over 3. That's 1/3. Okay? And this is, of course, 4 minus 1 is going to be 3. So that's 2/3 minus 1/3, or 1/3, divided by 3. That's 1/9. Okay? So the average rate of change of this function over this interval is 1/9. And now I simply need to figure out where this derivative is equal to that average rate of change. So I have to just set them equal to each other. So I have 2 over x plus 2 squared is equal to what? Okay, well, let's do 1/9. And of course, that right there is just a proportion. I can cross multiply if I want to in order to get down to where I can solve for x. And so I'm going to have x plus 2 squared is equal to 18. Okay. And so I have x plus 2 is equal to, remember the plus or minus, 3 root 2, or x is equal to -2 plus or minus 3 root 2. Well, one of those places is in the interval, and one of those places is not. Okay. The place that is not in the interval is -2 minus 3 root 2. Okay? But x is equal to -2 plus 3 root 2 actually is in the interval. And we can go ahead and actually see what that is. Okay? let's do negative 2 plus 3 root 2, and that's 2.243, okay? So 2.243 is the point in the interval. And you could actually graph this, right? You could actually, take that value right there, create the tangent line for that, plug it into y2, and actually show the secant line in y1, or actually show the function in y1, the secant line in y2, and the tangent line in y3, and actually see the fact that they are parallel. Okay, or you can just go back and look at it numerically. Okay, when I plug this value into the derivative function, I'm going to get 1/9. So at that moment, at 2.243, I have a slope of 1/9, just like I do as the average rate of change on the whole entire interval. Okay. Now, that was a lot of backtracking and trying to sort of draw out where the mean value theorem comes from, but you know me, I want to make sure that you understand where it comes from, because if you understand where it comes from and why it exists and what it's trying to say, you're more likely to remember it, right? And if you can make sense out of it, and it's not just a mere method or a procedure, you're more likely to remember it and understand it and actually appreciate it for that matter. We'll go ahead and do a couple more videos. I don't know exactly how many. I'll just do some examples until such time as we sort of run out of steam. In the next video, I am going to introduce a corollary to the mean value theorem called Rolle's theorem, but it's basically just a specific instance of the mean value theorem. So you have that to look forward to. And actually, it almost, like, you don't really need to use it at any point, but most books actually mention it, so I figure I will. So yeah, be looking for another couple of videos on this, and as always, if you have any questions, please do email me.